very good afternoon to all of you. Indeed, it is an honor and privilege to share the stage with highly accomplished people from different domains. And all the talks so far, apart from Prof. Thomas, was more abstract, was at a higher level. And in line with the previous presentation, this one is also a very specific talk. And I am Nishant Kumar. I'm a PhD student at the Singapore ETH Center. And I did this work in collaboration with my fellow PhD student Yatao Zhang and our supervisor, Prof. Martin Robel. And this is titled Explaining Road Network Resilience Using Spatial Variations of Network Topology. And we specifically focus on Singapore as a pilot. So first I discuss what is resilience. In simplest terms, resilience is the ability of a system to bounce back after a disruption. And this is what we are interested in modeling at FRS. To begin with, I have this impactful, rather sad image of a traffic accident from Singapore, PIE, the Pan Island Expressway. So someone probably died in that, someone was injured, and then there's a traffic jam. So given our background, we are sadly not fit enough to save the lives. Rather, what we can do is to reduce the time required to deploy life-saving services and clear the congestion as soon as possible, so that everything that can be done faster. So as transportation researchers, that is our best bet. So here I have a typical resilience curve of an infrastructure. So there is a disruption, and then there is a loss of serviceability, and over time this recovers. And we are interested in improving the recovery rate of the system, and that is a more resilient system if it can recover faster. So on similar lines, a traffic accident presents us with a similar kind of curve. There is an accident, and then there is a loss of traffic flow, and so several emergency response teams are dispatched, like the ambulance, the police, and then there's a control room involved, and finally the congestion starts to clear up. This also involves the people who make their own decisions. They change routes. They use some route-based services like Google Maps and switch to a different route. Finally, we have the congestion cleared. And the duration between the initial accident and the point where the congestion was cleared, that we refer to as the total incident duration in this study. And that is what we are interested in modeling. So what is the motivation behind this study? Well, yeah, so in the previous talks, we heard a lot about scale. So we are, as modeling city-specific variables, we are interested in the scales. And what we are particularly good at from a technical researcher's perspective, that we always take the city, we split it into grids, and we do our computation. First of all, it reduces the computational complexity. Secondly, it makes things parallelizable. So we like doing that. But the question which we often face is that how many grids should we split the city into? And this is what we try to address in this research. So we take the city, and we take Singapore as our pilot. We split it into uniform grids. And every grid is a road network. It has some graph features. And with those graph features, we try to predict what is the expected congestion clearance time of that grid. And then we vary the size of this grid from very fine to very coarse. And we expect to find a sweet spot which helps us model this easily. So that is the first part. And in the second part, which is the research question 2, we explored the possibility of allowing for heterogeneous grids, moving away from the uniform grids, and then have a segmentation of the city, which can help us better model the TID and hence reduce the congestion clearance time. So here I have some images of how the road network features vary across Singapore. Features like edges, the nodes, number of intersections, average length per intersection. So this is a very nice motivator to show that these road features, they vary across the city, and we start our research with this. So each of these images, they become a feature in the X feature, and then Y is our TID, the total incident duration. So to summarize, here I have our algorithm in 4 steps on the right, in the right box. So first we split the city into uniform grids, and then we organize those grids, each size of the grid, that is, we refer to them as scales. We organize them into trees. And finally, we iterate through them, we find the best scales. And then in the final step, we propose a region merging algorithm to find heterogeneous to find regions of, to find continuous regions, which help us better model the TID. And on the left, I have a summary of our data. Our data was collected using a commercially available here traffic API. The unique thing about this is, in terms of what previous speakers said, that we are at a point in time where we have challenges, but we have good data available. And this is a very good example of this. So this whole API is available for every city in the world. So that means our entire method can be shifted tomorrow if we want to a different city. And this is something that we are really working on at FRS, that all our current research is targeted at making it flexible and transferable to a new city. And our best scale comes out to be around 80 cross 80. So that translates to 250, around 250 meter square grids in the city. And that gives us the best goodness of fit if we try to predict the TID using the road network features. And this is more of a computational trick that we did. We organized the scales into trees and so that they fit in when we split them. And so at the scale of 80 cross 80, here we have, so for the next step, we want to look for the non-uniform grid. So we start with the clusters of accidents in the original uniform grids. And in those clusters, we do a connected component analysis. We find all the regions which are connected. And from there, we allow our split and merge algorithm to go and to search for nearby connected regions and ultimately segment the city. So the segmented city looks like this. Yes. So we start with those cluster centers and we allow to merge with the nearby regions. And the merging criteria is determined by network connectivity, which is the most important aspect, because we are interested in regions where an ambulance or a police vehicle stationed near the expressway can be easily deployed. So within those whole region, so if you pick up any color, so the whole region is connected. So that means a police vehicle around anywhere in that region can reach the site very fast, and this reduces the time to deploy. And then we also have another notion of topological similarity, where we argue that similar roads, topological similarity, usually the similarity of road features. This implies that roads which have similar number of terms, similar width, they should share the resources. Because if we are talking about very narrow roads, so probably they need narrower road clearance vehicles. So that is what we include in our merge criterion. And here I have a summary of my results. So before merging, we had absolute percentage of 4.28 and it decreases to 3. Honestly, these are not the kind of results that we were hoping for initially, but that just implies that this problem is more complex than we thought initially. And what we are doing right now is that instead of having a global goodness of fit, we are going into the details and we want to look at clusters inside the city where there are more and less accidents, and can we model that better? So with this, I have come to the end of my talk. I hope you enjoyed it, and I'll be open for questions later. Thank you.
Thank you, Mr.